You've got magic in your hands, just waiting to be found. Don't need to understand it and it all, just let it come around. 'Cause you've got magic in your hands, and I can show you how.
Hello everyone, welcome to the lab explanation video for Lab 1.2, Music Generation with Recurrent Neural Networks and TensorFlow. What you just listened to was a piece of music generated by one of the state-of-the-art models. And today, in our lab, we are going to be exploring the foundations that allow us to generate a piece of music using an Irish folk music dataset. As an example of one of the pieces of music we will be able to generate, I went through the lab and created this piece of music. It continues for about another 2 minutes, but it is an illustrative example of what we are going to be able to create. So to go through the lab, you can go to the inspiredk.org website and click on the AI Program Labs button. This will take you to the inspiredk.org GitHub, where you can navigate to the MIT Intro to Deep Learning repository. The lab we are going to be going through today is adopted from the MIT Introduction to Deep Learning course, and I edited it under the MIT license. Once you go into the MIT Intro to Deep Learning repository, you can navigate to the Lab 1 folder and the Lab 1.2 Music Generation with RNNs and TensorFlow Python notebook. From there, you will be able to click the Run in Google Colab link to go through this lab on a platform called Google Colab, offered by Google to allow anyone with a Google account to use high-power GPUs for free. So now let's jump into the lab. First, we are going to start by downloading several packages and dependencies that will allow us to work on this lab. It's going to take about 2 minutes, so while it is downloading these dependencies, I would like to introduce the MIT Deep Learning package built by the instructors of the MIT Introduction to Deep Learning course. This package installs several different dependencies, including TQDM for textual progress bars and NumPy for multidimensional, highly efficient arrays. Additionally, each folder inside of the MIT Deep Learning package provides several built-in functions that abstract away some of the more complex coding functions inside of our lab and allow us to focus on the learning process for neural networks. For our lab, we have several different built-in functions, including the load training data function, which takes our Irish music dataset in the ABC notation, which is a type of textual music representation that can be converted into .wav files to be listened to in audio. Then the extract song snippet takes this .abc file and extracts only the song portion from each song in the file, and it takes away all of the excess data about each song. Then we have the save song to ABC function, which allows us to take one of our generated text songs in ABC format and saves it to a .abc file. Then we use the ABC to WAV function to convert a given ABC file into a WAV format. Then we use the play WAV function to take a WAV file and play it built-in inside of the Google Colab console. Then we combine these three functions in the play song function, which uses save song to ABC to take a generated song and convert it to an ABC file, the ABC to WAV function to take our ABC file and save it in a WAV format, and then if the song is valid, we'll use the play WAV function to play our song built into Google Colab. Then the play song function is used by the play generated song function for every generated song we have in our final text. So we use the extract song snippet function to take our generated text and extract the song portion from each song. And then if there are no generated songs that are extracted by extract song snippet, we get an error message that no valid songs are found in the generated text. However, if there is at least one song, we can use the playSong function to play each song. However, if none of the songs are valid, we get another error message that says none of the songs were valid. Finally, we have three different functions: test batch func types, test batch func shapes, and test batch func next step, which allow us to ensure that all of the functions we will be writing to extract random parts of the dataset for training are being created correctly. So now that all of the dependencies and packages have finished downloading, let's jump into the dataset. First, we are going to download the dataset using the load training data function from the MIT Deep Learning package, and we are going to extract the first song to see the format of our ABC file. There are 817 songs in our dataset, and as an example, our first song has an index entry of x at 1, a name entry at t:\Alexander's, as well as much more metadata, as well as the song itself in ABC format. We can see that there are different characters from A to G, uppercase and lowercase, as well as several different special characters that allow the ABC notation to be correctly formatted. Now let's use the playSong function from the MIT Deep Learning package to convert our ABC notation song and listen to it. So it's going to take a few seconds in order to play our song, and we will be able to see it inside of our console. Now let's listen to the first few seconds. The song continues for about another 55 seconds, and this gives us an example of the type of music we are going to be able to generate. After that, now we can process all of our songs, which are currently in list format, into a single string to find all of the unique characters to provide our model with guidelines on what it will be able to generate. So we're going to use the .join function to take all of our songs and separate them by several enters, and then we are going to find the unique characters in that string. We see that there are 83 total unique characters inside of our dataset. So far, we have covered the different dependencies and packages that we imported for our lab to work, as well as the dataset, including its format and what types of songs we are going to be listening to. So now let's take our dataset and process it to become numerical, as neural networks do not take textual inputs, and they can only represent numerical inputs. So first, let's create two different mappings, including the character to index and index to character mappings. The first character to index mapping will assign each unique character in our vocabulary to a specific index, and the index to character mapping will give each of our characters from the vocabulary its own specific index, so we can convert from a character to an index and an index to a character. Now let's examine the character to index mapping, including its first 20 characters and their indices. So I forgot to download to run the first code block with our mappings, which is why we received an error that the name char2idx is not defined. So let me run this code block, and now we can see the first 20 characters and their associated indices. First, the new line character is associated with index 0, the space character is associated with index 1, the exclamation mark character is associated with index 2, and so on for all 83 of our unique characters from the vocabulary. Now that we have our character to index mapping, we can create a vectorize string function, which will take a given input of a string and output its numerical representation. So first, we're going to use our character to index mapping on each character in our string, and we will take all of these numerical representations and put them in a NumPy array to have efficient operations. Then we are going to output this NumPy array, and we're going to run this function on our entire song dataset. To see an example of how our songs from textual format are converted to numerical representations, let's look at the first 10 characters from the original songs versus the vectorized. We can see that originally, the song dataset was x:1, new line t:\Alex, and it was converted to a list containing 10 different integers, where each represents its own character from the first 10 characters, and they are all unique. Now that we have covered how we can convert our character inputs to numerical representations for our neural network to understand, let's go through how we can create different training inputs and expected outputs with our model. We're going to define the getBatch function, which takes an input of our given vectorized songs, a seq length, and batch size. This function will be able to create batch size sequences where each sequence is of length seq length. First, we get the length of our entire vectorized song string, and we use the np.random.choice function to find batch size starting indices in a range from 0 to our entire vectorized songs. Then we take each index from these randomly chosen starting indices and create an input and output batch. Our input batch contains all of the sequences that will be inputted to the model, and our output batch takes these inputs and they shift them over by 1, so our model can use these outputs to predict the next most likely character and compare its prediction to the actual expected output character. Now let's take our input and output batch and use np.reshape to convert them to the correct shape for our model to understand, where each character and each sequence is given its own specific place. Now we have x and y batch based on our input and output batches respectively. Let's use the getBatch function for a given testing arguments of our entire song dataset for a sequence length of 10 with a batch size of 2. Let's use the test batch func types, test batch func shapes, and test batch func next step functions from the MIT deep learning package to ensure that our getBatch function is working correctly. When we run this block of code, we can see that all of the tests are passed and our getBatch function is working correctly. Now, let's examine how the x and y batches compare by getting a single batch of sequence length 5 from our dataset. We can see that at the first step, step 0, the input is of index 82, or the bar, and its expected output is the index 29, or the character D. And step 1, that expected output is becoming the input, and we have an expected output of index 26, or A. This continues for every step throughout our x and y batches, and this allows us to take an input to our model, get a prediction, and compare it to that expected output so we can train our model to get closer to having more likely expected outputs so it can generate correctly formatted music. Now that we have discovered how we can create different inputs and outputs to train our model, let's define the actual recurrent neural network itself. So let's examine this diagram so we can see how the model will be defined. For every character in each sequence for our batch size sequences, we take our input character through an embedding layer to convert it to a character embedding that has size batch size by embedding size. This is so our model can have a highly dimensional numerical representation to convert it eventually to probabilities of the most likely next character after this input. Then we will use a type of recurrent neural network called long short-term memory, or LSTM, so we can retain a lot of previous information about our song that we generate to incorporate song elements correctly. Then our LSTM output is of shape batch size by LSTM units, where LSTM units is the number of neurons in our LSTM layer. Then we take this output through a dense layer and get an output called logits, which are really just the probabilities of the next most likely character in size batch size by vocabulary size, as each character in our vocabulary will have an associated probability. Now let's define our recurrent neural network using code. First, let's start by defining the long short-term memory layer using the built-in TensorFlow LSTM layer. We're going to take an input of RNN units, which will be how many neurons our layer has, and we will set several different parameters to ensure our model works as expected. First, we have return sequences true to ensure that our model returns an output. Then we have recurrent initializer of Clairaut uniform, so we can have a correctly shaped output, and we use a recurrent activation function of sigmoid, as our problem is working with probabilities, and the sigmoid activation function is the best activation function for probability problems. Then we set stateful and unroll to true to ensure that previous predictions from our LSTM layer do not interfere with future ones, and our model works as expected. Now, let's create the build model function, which will take our LSTM as well as an embedding and dense layer to create our entire model. So let's start by taking an input of our vocabulary size, embedding dimension, RNN units, and batch size. Next, let's use the sequential API built into TensorFlow to chain together our layers, starting with the embedding layer, which takes an input of vocabulary size and returns an output of embedding dimensions. Then we take this output and send it through our LSTM with the given input of RNN units, and take those outputs through our final dense layer to get the probabilities of output vocabulary size, so each character in a vocabulary has its own respective probability. So let's create an example model with our vocabulary length, an embedding dimension of 256, RNN units of 1024, and batch size of 32. Now let's use the .build function on our model to build our model to have batch size by sequence length to ensure it will work correctly. Now let's see how our recurrent neural network model looks by using the model.summary function to see how each layer is working. So we can see that our embedding layer has an output shape of 32 by 100 by 256, or batch size by sequence length by embedding dimension. Our LSTM layer has output shape of 32 by 100 by 1024, or batch size by sequence length by recurrent neural network units. And the dense layer has a output shape of batch size by sequence length by vocabulary size, which is 32 by 100 by 83. Let's get some example predictions from our model by creating a batch with 32 sequences, each of sequence length 100. So let's pass in the inputs for a given prediction, and let's examine the shape of our inputs versus the output predictions. So our input shape is 32 by 100 batch size by sequence length, as expected from our getBatch function, and the prediction shape is 32 by 100 by 83, which is expected according to our model summary. Now let's examine the predictions that we have from our untrained model by using a probability distribution to take each of the logits and find which character they are predicting to be most likely next, and chain all of those characters together to get our output. Now let's see what our input is compared to the next character predictions. Our input seems to be very logical in the sense of a ABC notation dataset, while our next character predictions are extremely random. This is because we now need to train our neural network. First, let's start by creating a loss function called compute loss that will create a value called the loss, comparing our expected outputs versus the actual predictions, so we can use that loss value to make our model have a higher accuracy. We're going to use a type of loss called sparse categorical cross-entropy, which is used for probability problems such as ours. We're going to give it our labels, which are our expected outputs, and our logits, which are the most likely next characters predicted, and we will set the from logits parameter to true in order to make sure our loss is being calculated based on the expected characters versus the actual outputted characters. For our initial model, let's see what the loss is between our prediction compared to the actual output. We see that our loss is about 4.4, which is extremely high for a neural network like this, and we want to aim for a loss as close to 0 as possible. Now, let's define some hyperparameters or parameters for our model that will be used to define everything in the same way so our model correctly trains, and we can experiment with these hyperparameters to see which works best and which generates the correct music. So first, let's create a vocabulary size variable called len of vocab to create a storage for our vocabulary size so we can have increased accuracy in the future. Next, let's define our model parameters using the params name and create a dictionary including the hyperparameters of number of training iterations, which I set to 10,000, batch size of 8, which I set to 8, sequence length of 125, a learning rate of 5e-4, an embedding dimension of 256, and recurrent neural network units of 1024. Finally, let's create a file in order to store our model's weights so we can have each of the training iterations that we have saved to our file so we can choose the best weights and ensure that we have our model with the highest accuracy. Let's use these hyperparameters and train our model. First, we are going to build our model with our vocabulary size, embedding dimensions, RNN units, and batch size. And we are going to create an optimizer called Atom with our learning rate, which will take our loss and compute a value called the gradients, which will allow us to take our model a step closer towards lower loss and higher accuracy. Now let's define the train step function, which takes an input of x and y. So we can use a method called gradient tape to get our predictions from our model based on the input batches, compute the loss between the expected outputs and the actual predictions, and then compute a value called the gradient based on all of the operations done in our tape, and apply our gradients to the model using the optimizer, as well as provide it with the hyperparameters to ensure our model is correctly applied to with our gradients. Now let's use this train step function so we can train our model for our set number of training iterations. First, let's start by creating a list called history to store all of our losses for graphing purposes. Then let's create a type of plotter called periodic plotter from the MIT deep learning package, which will allow us to see the loss trend as it is training. Then, using the TQDM library, we can clear any previous textual progress bars and create a new progress bar for all of our training iterations. Then, for each iteration in our training iterations, we can get a random x and y batch with our sequence length and batch size, and use the train step function to get our loss. This will allow us to train our model towards a higher accuracy, and we can also take our loss and add it to the history list and plot that history list to see our overall trend of the loss. Then, every 100 iterations, we will save the weights to our previously defined checkpoint file, so that way if training is ever interrupted, or we see better weights in a certain point in the training process compared to the entire training process, the model will be unaffected and we can continue to generate music. Finally, when training is over, we can use the save weights function at the end to save all of our final weights to the checkpoint prefix, so if training is not interrupted, we can make sure our best weights are saved. Now our model is going to train based on all of the things that we have defined, and we are going to be able to see a outputted graph based on each of the losses that we get for every training iteration. This will take about 15 minutes, so I will speed the video up here, and we will come back so we can generate some music and listen to it. Now that the model has finished training, in about 14 minutes and 44 seconds, we can see that it has achieved a loss very close to 0. We can now take our best weights that we achieved from the training process and build a new model in order to generate our very own music. First, we're going to start by taking our weights and building the model with our vocabulary size, embedding dimensions, and recurrent neural network units. Now, we're going to use a batch size of 1 and build our model with a shape of 1, so that way it can generate one character at a time to create a full generated text in ABC format that we can convert to listen to. Additionally, we're going to use the load weights function on our checkpoint file so we can take the best weights and have our model with the highest accuracy for the best generations. If we look at a model summary for our new model, we can see that now we have batch size by none by a given parameter for every layer. So for our embedding, it is 1 by none by 256, where 256 is the embedding dimension. The LSTM has 1 by none by 1024, which is the number of RNN units, and our final dense layer has 1 by none by 83, where every vocabulary unique character has its own probability, and the vocabulary size is 83. Let's look at this diagram so we can understand how our prediction procedure is going to work. We're going to start with a given start string and feed it through our model to get the most likely next character probabilities. Then we will use a probability distribution in order to get the most likely next character and send it through the LSTM again to get the most likely next character and continue for a given set amount of wanted generated characters. To do this, let's create the generate text function, which takes our model, a start string, and a generation length defaultly set to 1000. We're going to start by taking our start string and converting it to numerical format using our character to index mapping, and then we're going to change its dimensions to account for the size of our start string. Then we're going to create an empty list called text generated to store all of the characters that we generate. Next, we're going to take our LSTM layer and reset its states to ensure that its previous predictions do not interfere with the new predictions that we have, and we're going to clear all previous textual progress bars with TQDM to create a new progress bar to track our generation progress. Then, for every given iteration in our generation length, we are going to get the predictions from our model using the given input of the start string, and then use a probability distribution to get the most likely next character. After that, we will add that next character to our input in addition to the start string, and we will add that character associated with the predicted index to our text generated list, and finally return the starting string in addition to the entire generated characters. Now let's use this function that we have for our model with a start string of x for a generation length of 1000. We use the start string of x because most ABC notation files start with x, and this is the best, most common start string we can use. It will take a few seconds to generate all 1000 characters, and once it is done, we will be able to play back our generated music. So it took about 9 seconds to complete generating the text, and now we can use the extract song snippet function from the MIT deep learning package on our generated text to get all of the songs in list format. Then we can assign each song to a given index, so that way it can be saved to the file section of Google Colab with each song having a unique name. For each ABC notation song, we use the play song function from the MIT deep learning package to convert it to a .wav file, and if it is valid, we can print that we have generated a song at the given index, and we can use the IPython display, which is used for built-in display for Google Colab, to create a play button inside of our console output for our .wav file. Finally, we can save our .wav file to the Google Colab Files section, which can be accessed on the leftmost sidebar on the folder icon, where all of the saved songs will be there. Let's run this code block and see what songs we have been able to generate. We have been able to find 3 songs, and so far we can see that each song has its own respective play button. Let's listen to the first few seconds from each song. So that was our first song, which seems to have a very fast tempo. Now our second song is a little bit longer. That was the first 10 seconds of our second generated song, which seems to have a slower tempo than the first. And our final longest generated song is about 2 minutes. At this point, I would like to go through a quick review of the entire lab. First, we started by downloading all of our dependencies and packages that we need for the lab. Additionally, we took a deeper look at the built-in MIT Deep Learning package created by the MIT Introduction to Deep Learning course. Then we downloaded our dataset using the MIT Deep Learning package and examined the format of all of our songs, and we found our unique vocabulary with all of the unique characters inside of our dataset to put constraints on our model for generation. Next, we processed our textual dataset to convert it to numerical representations using a vectorizing function as well as character to index and index to character mappings. After that, we used a getBatch function in order to find training input and output examples to train our model on to achieve higher accuracy. Then we examined how these batches work and why we need an input and output batch for our training process to have better outputs with more likely to be playable songs. Then we examined the recurrent neural network we are going to be used, which is based on the long short-term memory type of RNN, which is extremely critical for applications where we need to retain a long memory of previously generated characters. And we defined a recurrent neural network using built-in TensorFlow layers, as well as the sequential API to chain together all of our layers. We created an example model, and we examined how it is created and what kind of predictions we received. We saw that our predictions were extremely nonsensical, and we found that we needed to train the model. To train our model, we first defined a loss function using sparse categorical cross-entropy, which is useful for our probability problem of predicting the next character, and we saw that our example first generation had a loss of about 4.4, which is extremely high and means that our model has very low accuracy. Then we defined several hyperparameters for our model, including the number of training iterations, which can be increased or decreased to change the amount of time our model needs to train, the batch size and sequence length to change what our model is going to be trained on, including how many random sequences we have and the length of each random sequence, the learning rate of 5e-4, which is a mathematical representation for an extremely small number, and it needs to be set very small, as for optimization of our model, we need to have a very small rate of change based on the inaccuracies of our model to take a step towards increasing the accuracy. Then we had our embedding dimensions, which we used in our embedding layer of the model to ensure that our inputs are correctly converted to a numerical representation. And finally, we defined RNN units, which is the number of neurons our LSTM layer has, which will dictate how much operations it performs on our dataset and how much time the code will take to train. Then we built our model using our hyperparameters and as well as defined an optimizer called Atom, which uses adaptive learning rates based on our initial learning rate to have a faster descent towards a lower loss. And we defined a train step function to compute the loss, get a value called the gradient, and use that value to take our model a step towards lower loss. Then we looped using this function for our set number of training iterations, which took about 14 to 15 minutes, and we achieved a loss very close to zero. Finally, we examined how we rebuilt the model using the best weights we achieved with the lowest loss, using a batch size of 1 for our generation task, and we used that model for our prediction of the next character procedure to generate 1,000 characters in ABC notation, which allowed us to listen to 3 beautiful songs. I highly encourage you to go through this lab and go through it, completing all of the to-do blocks, so that way you can gain a deeper understanding of how recurrent neural networks work, as well as how you can implement them in code. Additionally, I recommend that you experiment with different hyperparameters to see which ones create the most and best songs. To do this, consider how the number of training iterations can affect your performance. What would happen if you change the dataset for a different notation besides ABC, or perhaps different songs? And finally, if choosing a different start string for our generation task besides X could impact our performance. Again, to find this lab, you can go to the inspiredk.org website and click on the AI Program Labs button to take you to the inspiredk.org GitHub. And from there, you can navigate to the MIT Intro to Deep Learning repository and the Lab 1 folder inside of it. And finally, you can go to the Lab 1.2 Music Generation with RNNs and TensorFlow Python Notebook and click the Run in Google Colab link so you can go through the lab with Google Colab for free GPU access and fill in all of the to-do blocks, which will give you a deeper understanding of how the lab works, so you can be able to possibly build your own recurrent neural networks in the future for your own tasks. Thank you for joining me in this lab explanation video.